So today we're going to continue what we stopped last lecture, which is Carnot. We in section 6.7 we said that we have Carnot cycle. This is lecture 11, but we're going to start over from lecture 10 again, which is Carnot cycle. So Carnot cycle is the most ideal cycle you will ever have. It is like this. It's 4 stages. It is 4 reversible, isothermal, adiabatic, isothermal, adiabatic, as is shown here in PV diagram, TV diagram, and TS diagram. Reversible adiabatic, there is no heat and it's reversible. It means there is no change in entropy. Just for now, make delta S equal 0. There is no change in entropy. That's why we said, and if you plot the TS diagram, between 2, 3 or 4, 1, you have constant S. So this line, this process or this process going upward, both of them are isentropic. It means S equal constant. So this is look like the S equal constant adiabatic process. S equal constant in the PV diagram, S equal constant in the VTV diagrams. While they are vertical lines in the TS diagram. That's why sometimes the TS diagram is the best, one of the best diagrams ever, because it's just a rectangle. Okay? The most important thing here, guys, T1 equal T2 equal T high, for example. Hey guys, everyone is following me?
Yeah.
So T1 equal T2 equal T high. This temperature is called T high. T high, T high. T1 equal T2 equal T high, TH. While the lower temperature of the system is T3 equal T4 equal T low, TL. So we have two temperatures. Let's say 1000 Kelvin and let's say 300 Kelvin, for example. This is the maximum temperature and the minimum temperature of this system. In reality, guys, ideally between these black lines, let's say here, this is a PV diagram, is exactly this is the maximum, let's say, power you can get. But in reality, it's smaller, like the pink color. What you get, it's a little bit smaller. So remember, 1, 2, reversible isomer. 2, 3, reversible adiabatic. Read here and follow the line. Reversible isothermal, temperature constant. Reversible adiabatic, S is constant. Reversible isothermal, temperature is constant. Reversible adiabatic, S is constant. This is in the PV diagram, TV diagram, and finally TS diagram. Okay, let's say what is Carnot cycle is. This is called Carnot cycle. It's a very ideal process. It does not have any losses. Okay, guys, any questions so far? So we need to know how to draw a constant line in a curve, like in PV diagram, TV diagram, any one of these. You need to know how to draw the constant line. For example, in PV diagram, where is the constant volume? Vertical. This everything here is gas. TV diagram, where is the volume constant? Vertical. S diagram, where is the constant volume? It's kind of slant like this. This is called constant volume. So the volume here is the same as here, but different here. However, the constant pressure here is horizontal. The constant pressure here is kind of increasing with temperature. The constant pressure here also, I think, increasing with temperature. While the pressure, the TV, PV, pressure here is horizontal, pressure here is increasing, pressure here increasing. For example, what else? Temperature. Constant temperature line here is horizontal. Here is horizontal, but here is decreasing. This is a constant temperature line. Okay? Keep those. We can go back and forth between them. So what is Carnot cycle is? We still in section this, but this is lecture 11 to the 22nd. Wednesday 22nd. So the Carnot cycle is the most. We are now lecture 11-1, page 11-1. The most efficient device or system or machine between two temperatures. So we have two temperatures. Let's say T high and T low. This is the most efficient cycle. This is the maximum efficient you can get. The most efficient cycle. There are two principles. Carnot principles. There are two principles for Carnot. Regarding exactly what I said here. Let's write with another color. The efficiency of an irreversible cycle or system or device, an irreversible system is lower than Carnot cycle. So Carnot cycle is reversible. It's always Carnot, always reversible. Always reversible. It's ideal. It has no losses. You can say lower or less than. You can say is always less than Carnot cycle. So if you have an efficiency of a system, it's always lower than, we're talking about heat engine, power plant, always than Carnot cycle, which is the ideal, which is like no losses, the most efficient, reversible. So all these the same meaning. Carnot cycle, ideal, no losses, reversible. This is R. This is reversible. Reversible. Any question, guys? Any question, guys? Any question? Hello? Hello? Can you hear me, guys?
No questions.
No questions.
Good. So this operates between two temperatures. That's better to make it general. So if you have temperature high, you need to mention that. Why? Because if you have two temperature, let's say, for example, the last one is better. In the TS diagram, you have, this is the Carnot cycle. You have 1, 2, 3, 4. Between T high and T low, if you have other system, it will be always smaller, like this, something like this. Something in between. But if you have another temperature, you can get bigger. But if it operates between only two temperature, T high and T low, the efficiency must be less than the Carnot cycle, the most efficient cycle ever. Carnot is a reversible cycle. Reversible means the most efficient cycle. That, for example, you paid, let's say, 100 joule, you took the efficiency of 100 joule. Some of them already wasted, yes, but you got the most efficient from this 100 joule. You don't have other losses like friction, non-constrained gas. You have no problem with your system. So you have reversible process. If you have the efficiencies, this is the second principle, double I. The efficiencies of two cycles, two reversible cycles, reversible, like Carnot cycles or systems, operate between two temperatures. So we have two systems, both of them between the same two temperatures. They have the same efficiency. The efficiency are the same. Are the same. What does it mean? What does it mean are the same? The efficiencies are the same. What does it mean, guys? I'm gonna draw it for you again here. Another one, like this one. PV diagram, for example. In the PV diagram, if I plot for you the PV diagram, PV diagram, we said this is T high, for example, and this is T low, for example. This is one. Let's talk another color. Let's say two cycles. We have two cycles, guys. Two cycles. We have red and green, for example. So let's say the red is here, started here. This is T high, one temperature, and this is T low, one temperature. The red started here. This is one. This is two. Then three. Then four. Go back to one. This cycle one. Exactly like there. Constant temperature, constant entropy, constant temperature. So reversible isothermal, reversible adiabatic, reversible isothermal, reversible adiabatic. This is a PV diagram. If you plot this in the TV diagram, it will be, this line will be horizontal. This lines will be horizontal. So this is the PV diagram, the first cycle. The second one, this one. Where do you want to start, guys? Here or here or here? Anywhere. Pick up any point. Let's say it started here. Here.
Professor, can you move the camera a little bit? We can't see your writing on the left.
Okay, I'm sorry. Yeah, you see, supposed to say that, guys. So the point one here. As you can you see now, guys?
Yeah.
So I pick up two colors, red and green. The red one, I started here. It's the PV diagram. 1, 2, 3, 4, 1. 1. The 1, 2, reversible. Everything is reversible. Reversible isothermal. Reversible adiabatic. Reversible isothermal. Reversible adiabatic, and so on. This cycle 1. This is cycle 1. Cycle 2, he said no. Let's start with another one. Let's take color green. Let's start it, for example, here. Start anywhere. This one. Then go to, for example, 2. Let's say 1 dash, 2 dash. Then 3 dash. Okay? Then let's say 4 dash. Then I think it's here better. 4 dash. So this is our cycle like this. So we have one green, the bigger, one red is a little bit smaller. Okay, guys? Okay, guys? Any questions?
No.
Efficiency of the first cycle exactly equal the efficiency of second cycle. Cycle 1 and cycle 2. Why they are the same, guys? Because they have the same higher temperature and lower temperature. T high in first cycle equal T high second cycle. T low first cycle equal T low second cycle. Their efficiencies are the same. Cycle 1, cycle 2. This is exactly the second principle. So the second principle said the efficiencies of two reversible cycles. This is reversible here. Reversible cycles operates between two temperatures. The same two temperatures are the same. The efficiencies are the same. Okay, guys? Engines, cycles, devices. Okay? Any questions? Let's draw the same thing in Pence diagram. In Pence diagram. So let's draw the same cycle in Pence diagram. Let's draw 3 cycles. Represent this and this. How? Look at this. I have source, let's say T high. I have a sink here, reservoir. It has T low. So 2 reservoirs, high temperature and low temperature. In the first cycle, let's say I plot here the heat engine. Heat engine always like this. This heat engine. Let's say heat engine 1. Heat engine 2. HE mean heat engines. Heat engine 3. Let's say heat engine 1, for example, now reversible. This is reversible. This is reversible. This is irreversible. Irreversible. IRREVER, irreversible. Okay. So the first 2 are reversibles. The last one is irreversible. Okay. Maybe Q high here different from Q. Yeah, Q high here different from here. Maybe different from here. It's okay. Maybe like this system, one has lower, higher heat. Maybe this cycle can be here, very low here, very low here. You can say another cycle here, for example. Anywhere in this PV diagram. So maybe Q high is different. Let's say 1, 2, 3. Q low is the same. Can be 1, 2, 3. Even W net can be 1, 2, 3. So maybe the work from this different from this. Maybe the heat is different. I don't care. What I know that they have the same T high. They have the same T low. All of them. This is reversible, but this is irreversible. What do you think about eta 1, eta 2, eta 3? Eta 1, eta 2, eta 3, guys. What do you think from these principles? What do you think, guys?
Eta 1 is going to equal to eta 2.
Exactly. They are reversible. They are the same efficiency. They here are the same because the same temperature, but both are reversible. How about eta 3? Greater or smaller? It's irreversible.
Greater than, it's less than the
Exactly,
others.
less than. It's irreversible. So eta 1 equal eta 2, but it's less than. Eta 3 is less than. Make sense, guys? Make sense?
Yeah.
So let's move ahead a little bit forward until we go to Lord Kelvin suggestion, which is very good input for this problem. Okay. As you can see here, there is something, I'm going to remove those, but these principles are important for our cycles. We're going to see how they are important later, but for now, remember that always the efficiency of irreversible lower, irreversible always lower, but the efficiencies of reversibles are the same as long as T high is here is T high here, T low here is T high low here. I don't care about Q high, Q no for now, but if the T high and T low are the same between 2 cycles, and this is our reversible, efficiency are the same. If T high is the same as T high and T low is the same T low of 2 cycles, and one is reversible, one is irreversible, it means irreversible has lower efficiency. That's the conclusion here. There is something in section 6.9. Still, we are in continuity of this page 2. We're still in Carnot cycle generally, but also we need. So he said there is something called the temperature scale or thermodynamic temperature scale. there is something called temperature scale. It means the thermal efficiency, as you remember, if you remember, guys, we said it's W, for example, net out divided by Q high. If you have heat engine, what you want over what you paid for. So what I want over what I paid for, or it was 1 minus Q low over Q high. According to first law of thermodynamics, Q low plus W net equal Q high. So I can replace W net by Q high minus Q low, which is 1 minus Q low over Q high. It's also has something called temperature scale. It's a function of T high and T low, or function of T high over T low. It's a function, somehow function of T high and T low. It's called temperature scale in thermodynamics. Or Q high over Q low, which is this guy, function of Q high, T high over T low. We don't know what is this now, but he said there is some kind of temperature scale. If Q high over Q low as a ratio is a function of T high over T low as a ratio. So regarding this and this, let's say this is 300, this is 100 joule, or 3,000 over 1,000, over 30,000 over 10,000. This is a ratio. I don't care about the value of this or this. I'm talking about the ratio between them. They are function of temperature scale, function of, let's say, 1,300 or 700 and 290, for example, in Kelvin. Of course, every temperature is in Kelvin. This is in Kelvin, this is in Kelvin. So the ratio between the heat high and low are function of this. So we have Lord Kelvin, as Home Alone, you can remember Kevin, K-E-V-I-N. So remember this. So Lord Kevin, he was Home Alone. He said Q high over Q low equal T high over T low. He said use it exactly the same ratio. First order approximation. Q high over Q low equal T high over T low for only reversible. For reversible process. We do not gonna talk about the derivation of this. This is suggestion. This is a kind of an, I think he suggests that solution. He suggested this solution. Q high over Q low, reversible equal T high over T low. Now we can write eta thermal this way, guys. Eta thermal is 1 minus Q low over Q high. Can somebody tell me what is this here? What is over what?
T high over T low?
Nope. Q low over Q high. Q low over Q high equal to what? 1 minus what? Q low over Q high equal
T
1 minus
low, T low, and T high.
T low over T high. Perfect. The low with low, high with high. I reverse. Okay? So let's talk about this for a while. This is a very important equation in your thermodynamic life. The first one is always correct. The second one, only if it's ideal, if it's Carnot, maximum efficiency, if it's pure, if it has no problem, no losses. So the second form, this form, y minus T low over T high, is only valid if it's ideal. Reversible. Of course, you need to write reversible. Carnot cycle, ideal. But the first form, always correct. Y minus Q low over Q high, it's always correct. Okay, guys? Like, for example, Friday quiz, I'll give you a problem. It has part of it reversible, part of it is not reversible, like correct. So which one are you gonna use for the correct one, or always the real one? The real one, this always correct. This is no way. Real, ideal, anything is correct. But the other one is only if it's reversible, only if it's ideal, only if it's Carnot cycle. Let's look also another very important perspective. Look at this guy. We want this as maximum. We know this the maximum. I wish to be 100%. So let's ask you the question. If you want, guys, 100% efficiency, 100% efficiency, what should we do, guys? If you have Carnot cycle, even Carnot cycle is not 100%. Eta thermal, I want it to be 100%. What should I do, guys? What should I do? In this one, you have T low, you have T high. I want T low to be what? To what? If I have 0 Kelvin, I have exactly 100% efficiency. If just 1 Kelvin, it's not 100. 1 minus 1 Kelvin over T high. So I wish to have T low as small as possible. How about T high? I want it as maximum as possible. I will go. So there are two ways to make the efficiency 100%. By decrease the lower temperature to the minimum, which is, let's say, 0, which is impossible, or the other temperature, the higher temperature, to be infinity, the maximum you can get. Do you know what the temperature of the surface of the sun, guys? If you have sun, what the temperature here? Sun. You know what the temperature here, guys? It's about 7,000 Celsius or Kelvin. 7,000 degree. Of course, if you go to the core of the sun, hundreds of thousands of Kelvin or Celsius. In Earth, our surface is about 25 Celsius. If you go anywhere in the space, you will not find 0 Kelvin. You will not find this. It's impossible. 0 Kelvin means there is no molecular dynamics. Nothing is moving in an atom or in a molecule. Even this is hard, but it's still moving. Every molecule is vibrating. It has thermal temperature. Even it's 0 Celsius, like 273 Kelvin, it's still moving. 0 Celsius is still moving. The water or even solid, it's still vibrating. 0 Kelvin means there is no movement at all of anything. This is completely frozen, which is impossible physically. Okay, guys? Okay, guys? Guys, any problem? Let's
Nope.
take some question. Please read problem 676. Problem 76. Please, everyone, read problem 676. 676 in your book. I posted for you lecture 7, 8, 9, 10, and maybe 11. They are available online. I'm gonna remove this file Friday, so please download them now. Friday before the lecture, I will remove this file. Chapters 7 to 11 are available online, so please download them before Friday. Read problem 676, please. Go to the next book, read 676. It's a Carnot heat engine. Carnot can be heat engine, can be refrigerator, can be Carnot. When you hear the word Carnot, guys, remember the word? Remember the word? Remember the word?
Reversible and ideal.
Exactly. This is the most pure thing. There is no interest, something zero interest, something very, very pure. No worries, no problems. It's a most pure system, a reversible system. Okay? He gave us Q high and Q low and T low. Q high was 650 kilojoule. Q low was 250 kilojoule. And T low was 24 Celsius. He wants required A, T high, B, thermal efficiency. Okay. For the first required, it looks like so simple. So T high equal what? This solution. Guys, can you see the green or it's not good? Do you see the green or I can use other color?
I can kind of see it.
Okay. So this is better, I think. Let me some.
Yeah.
This T high over T low equal Q high over Q low. This is what Kelvin Lord equation. So I want T high. So T high equal T low times this, which is 24 Celsius times Q high over 25. What is the problem, guys? What is the problem here? Something is wrong. What is wrong?
Do we need to convert to Kelvin?
Exactly, exactly. Don't ever, never, ever substitute by Celsius. 24 plus 273. So now it's correct. If you have 0 Celsius, you will have 0 efficiency, 100% efficiency. That's wrong. Everything in absolute temperature is even called Lord Kelvin. So temperature should be Kelvin. That's even inherently or implicitly in the definition. So you can get T high, no problem. The T high can be found, no problem. Of course, larger than T low. It was, I think, 499.5. So T high was 499.5 Kelvin. How about eta thermal, guys? The second one, eta thermal. Which one, this or this?
First one,
Why?
because we already have QH and QL.
Exactly. That's smart way. That's very clever way. Both are correct. This problem is a reversible. For both form are correct. Yeah, this formula only correct in reversible. This formula always forever. But now I prefer this one because Q high and Q low are given. So it's preferred to use something with maybe you did mistake here. Maybe you use 24. So it's better to use the given. So 1 minus Q low over Q high. That's even much better for you. 650 over, no, 250 over 650. Of course, if you use this or this, they are the same correct number. But maybe you did a mistake in TI. Maybe you did a mistake by mistake, by something wrong. So you can get it here. The efficiency, which was 61%. That's huge efficiency. That's very, very huge. It's 0.615, which is 61.5%. This is really, really big efficiency. Okay, guys? Any question here? So try to minimize your mistakes. If you have two formulas, let's say in this problem, I give you T high and T low, but I want Q high. Let's say I give you T high and T low, I give you Q low. When you use this formula, use this better because T low and T high were given in the other problem. So always use the formula that has the more input. It has less opportunity for error or mistake. Okay? By the way, it doesn't matter with me. Even you have a mistake, like let's say when you calculate this, you get 299, let's 295. It's a mistake, but it's okay with me. But do not forget this. This is a significant error. But if you add it, but you have a mistaken kind of some error, it's okay with me. I'll accept that, but I will not accept to give me temperature in Celsius substitution, or even the output. The output is Kelvin, the input is Kelvin. Both are Kelvins. Lord Kelvin. Problem 695, 83 first, 83. Please read problem 83. So 83 was a geothermal engine. Do you know what geothermal engine, guys, means? So it's we wish to have power, electricity. We wish to have this by paying the lower cost. So some scientists are very smart. They said, okay, this is the surface of the Earth. Temperature, like they say 15 Celsius, 25 Celsius. If you dig in the Earth, here you may have a much higher temperature, may go to 300 or 400 Celsius, even more. Okay, some scientists were smart. They said, okay, how about this? If we put the tubes of water, go down and take some heat by heat exchanger here, then go back up. So all you need to do, pump it back up, just it's gonna go down by itself, then pump it up again. It has high temperature now. You can drive an engine, geothermal engine. That's very smart. So by this, almost with zero cost except that pump, take some electricity with almost zero cost. So you're gonna build this system, put water, take some power from here, drive the motor, and take some free electricity. This is few thousand kilometers, let's say 5 kilometers, somehow 2 to 5 kilometers. This is a very clever way to produce electricity with almost zero cost. Just some tube in the beginning, then you're gonna get them back. Put water or some cheap fluid, go back with high temperature, drive the turbine, give some to the pump, take some electricity for free. Good idea, guys, to produce electricity for almost free. Okay, guys.
Yeah.
So we have here in this problem, he given to you T high was 140 Celsius, a little bit smaller, 140 Celsius. T low was 20 Celsius. He wants the thermal efficiency of this cycle. So what is the thermal efficiency, guys? Can somebody tell me what is it? Calculate, please. It's supposed to be, if it's ideal, if it's reversible, it's 1 minus T low over T high. 1 minus 20 over 140. It's about what? How much, you guys? I'm waiting. Somebody is supposed to say something.
85.857.
Wrong. You're supposed to add 273 to both. So you see how much I said do not use Celsius. And in the exam, I'm sure this guy will not use the Celsius, but other guys, I'm sure he will use Celsius. You need to do now everything by your hand. You need to find your mistakes now instead of the exam. Okay, guys? Make sense now? Okay, guys, make sense? Hello?
Yeah.
Okay. Please read with me problem. And now we're gonna use problems. We're gonna rest by solving some problems. Read with me, please, problem number 2 in lecture 11. Open page 4, lecture 11, problem 2. It's a problem, is not in the book, so I got it for you. Okay, guys, read it. Everybody open the lecture, lecture 11, page number 4. It's called lecture 11, problem 2. In a steam power plant shown in figure 2, 1 megawatt is added to the boiler. It means this is Q high. Can you read with me, guys? Everyone, I will wait 1 minute to open lecture 11, page 4. Open page 11, lecture 11, page 4. Lecture, my notes, 11, page 4. It's 11-4. You will see lecture 10, 11, 12 in the same place, uploaded in the files. Lectures. So lectures 10, 11, 12 are given to PDF. Did everyone? Does anyone did not find it? That anyone, guys, did not find it? Does anyone? Did anyone did find it, guys? Did not find it? Ah. Okay, guys, did you all find it or not?
Yeah, I found it.
I wonder if the Carnot cycle applies in Minecraft. What does it mean? Hey Jay, what does it mean? You have the mic, you can talk. Somebody ask me question. Hey, can you hear me, guys?
Yeah.
What is Minecraft is?
It's a video game.
A video game. Do you think a professor in a school can play video games? Yeah, I saw it.
Yeah, sure you can.
Really? Oh, that's good. Cool. Okay, I'm gonna do that. Minecraft. I will buy it for my kids. Okay. Okay, let's back to life. By the way, I am originally a space engineer. If you don't know that, this is for your knowledge. Okay, so I'm gonna maybe play this. I like video games, by the way. That's cool. Anyway, so if you open back, please, page 11, lecture 11, page 4. I'm gonna read it with you. In a steam power plant, of course, as you can see, my English is so bad. So sorry. In a steam power plant shown in figure 2, this is a figure. So it has problem before that I remove it. I make only problem 2. Problem 1 was a little bit harder. It gives 1 megawatt, or actually 1 megawatt is added in the boiler. So can you see the boiler, guys? This boiler, it has Q high, even it's drawing on the boiler. It's upper left part of the boiler, this part. Actually, I can share it with you if you want. Do you want guys to share it with your screen? Guys, do you want to share the screen with you?
Yeah, sure.
Okay. I prefer, as I told you last time, please be prepared to read the lecture before the lecture. Like, for example, Friday night or Saturday, I will upload lecture 13, 14, 15. So you will have in advance these lectures. So let's now open lecture 11. page 4 of the lecture. Yeah, here. So as you can see, guys, it's a where problem 2 here. It says a steam power plant shown in figure 2, 1 megawatt MW is added in the boiler. 0.58 megawatt is taken out in the condenser. Condenser is kilo. This is called a condenser. The bottom part of the, usually we draw a high temperature on the top, low temperature on the bottom. If it goes temperature high to low, high energy to low energy, like turbine. So usually the lower energy parts draw in the bottom, the high energy part draw in the top. The turbine, the inputs in the up here, not in the bottom. The compressor is opposite, from the bottom to the top, because energy increases. So we have here a turbine. That's the way we typically draw parts or components of an engine. We discussed this before: condenser, pump, boiler, turbine. Condenser, pump, boiler, turbine. Condenser, pump, and boiler, finally turbine. So 0.58 megawatt is taken out. It means heat waste energy, dump it out of the system. The pump work is 0.02 megawatt. This work, the turbine, it takes some energy of the turbine, drive the pump, and the difference is W dot net. Comment W dot net. Okay. So find the plant thermal efficiency. I want eta thermal. If everything will be reversed, find the coefficient of performance of a refrigerator. So the first was power plant. Remember, the first was power plant. It means heat engine. So if you draw, for example, the Venn diagram, Q high, go to the heat engine, dumps Q low, and W net out. But he wants everything to be reversed. Reversed mean opposite, like opposite direction, reversed. It's everything actually ideal. So reversed, find the coefficient of performance, find COP of a refrigerator. Everything is reversed, find if it's this way heat engine, the other way is refrigerator. Let's take 6-minute break, come back at 11, okay? Or actually 9-minute break, okay guys? There is quiz today in the last lecture. So let's take 9-minute break. Okay guys?
Are we taking the quiz after the break, or are we like, is it at the end of class?
Of course, at the end of the class. We agreed with that. By the end of the lecture, we're gonna take 5-minute quiz, 10-minute upload by the end of the lecture at exactly 11:45. Okay?
All right, thanks.
No worries. Any question, guys? Last lecture, we're gonna continue now to solve a problem. Oops. Problem. I said problem what? Problem 11.2. So please open with me 11.2. We're gonna read it again. So it says, in a steam power plant shown in figure 2, 1 megawatt added to the boiler. This is Q high. 0.58 megawatt is taken out. It means Q low, rejected, dump it out. Remember these words because you're gonna see it or reject it in the quiz as well. But in terms of last lecture, lecture 10. The pump work, it's part of the work, derives the pump. And the rest of the work taken out as W net out. So the W dot turbine is a bigger one. Some part go to the pump, the rest go to the net out. Find the thermal efficiency. So you have Q high and Q low, so we can easily find the thermal efficiency. So W net is W turbine minus W pump, Q high minus Q low, or the thermal efficiency is just 1 minus Q low over Q high. 1 minus Q low over Q high. What's Q low? 0.58 megawatt. What is Q high? 1 megawatt. So what happened here, guys? Listen to this. This is very important. Guys, Q high and Q low were explicitly given, but in the exam, I may do this. Give you everything before the boiler, still before the boiler, and after the boiler. So you can use the first law of thermodynamics to get Q high. So first law of thermodynamics, open system for a boiler, turbine, compressor, pump, condenser, anything you can apply between state 1 before the boiler and state 2 after the boiler. This is before the boiler here, after the boiler there. So energy increases. Let's go coming inside with high pressure but low temperature. Going out with high pressure, the same high pressure, but very high temperature. Make sense? So I give you state 1 here. Can you see my mouse, guys? My cursor here? Can you see it?
Yeah, we can see it.
So before the boiler, I can give you the input to the boiler. 2 independent intensive properties. So you can know everything about this. If it's ideal gas or if it is steam, using steam table. The same for the output. I can give you 2 independent intensive properties. So you can get everything here and there. Q minus W equal delta H. You're neglecting the kinetic energy, neglecting the potential energy, just delta H. So you need H1, you need H2, so you can get Q, and there is no work in the boiler. So Q equal delta H, M delta H. Mass dot times delta H, change in enthalpy. You can get what, guys? The Q high. The same for Q low. I can give you 1 and 2. Last lecture, if you remember, we solved one problem through evaporator and we got the heat rejected, dumped in the air through this by giving state 1 and state 2. You can get Q low or Q high or anything, or even W turbine. If I give you a state here and a state here, 2 independent intensive properties on every side, you can get the work done by the turbine. The same for the pump. Correct, guys? So thermal efficiency by simply is 1 minus Q low over Q high, which is 42%. That's typical value. If you remember, Carnot was 60, 70, 50. So it's a little bit larger because Carnot is the most ideal engine. Okay, guys? So if you plot, okay, guys, do you have any questions?
I may have missed it, but do we just not factor in the 0.02 from the pump work?
Yes, this one. If I ask it about the work net out, you can this minus this. If I ask it for the W dot turbine, you need to add this. So this minus this, yes, it's exactly worked it out. For W dot out net is 1 minus 0.58, which is 0.42 megawatt. This is exactly the network, which is W dot turbine minus W dot pump. So if you want, for example, the W dot turbine, it is 0.44, 0.42 plus 0.02. It's much larger. Part of the work to drive the pump, to pump the flow, and the rest went out as W dot net. Make sense?
Yeah, that makes sense. Thank you.
No worries. So the network is 0.42, but the turbine is 0.44 because I add this value to it. Some part to go to this, so the net a little bit lower than W turbine, which is 0.42. This Q high minus Q low. So the equations are always valid. But when you go deep in the details, you see, some work drive this, the rest go out. So W turbine minus W pump equal W net. Okay? Okay, guys? So if everything is reversed means the heat engine is opposite, exactly opposite to the refrigerator. Heat engine, exactly opposite to heat pump. In refrigerator, what I want is Q low. So you can use this engine to cool some stuff, to cool it down by using Q low. To cool it down by using Q low, it means you put something in the refrigerator, it's lower or colder than what it was. So I took heat, dump it out. So everything is reversed. So it looks like the work is going in, the Q low going up, the Q high is going up. So still, this plus this equal this, but everything is reversed. This arrow is inward, kind of. Forget about this. The whole W net is in, Q low is in, and finally the Q high is out. So heat engine is like this. Refrigerator is opposite. So let's draw it back in the board, please. So as you remember from the Benz diagram, the same problem. In the Benz diagram, guys, we said if you have, this is a Q high, this is a heat engine, this is a Q low, this is a lower reservoir, the top reservoir, always the arrow going downward, this way, W unit. This is for heat engine, power plant, engine that produce work. This is Q high. So this plus this equal this, always Q high here, Q low here. This plus this equal this, net out. This is called heat engine. But we have another one. Let's draw it for other color, like refrigerator or even heat pump or refrigerator. So everything is reversed. Reversed means here Q low going up. Work net is in. I pay electricity to drive in. This is in. To drive the refrigerator. Then I dump Q high out. And this is T high, for example. This is T low. The same here. We can use T high and T low. So this is inputs. Now this is out. The same equation. Q high equal this plus this. W net in plus Q low. Here, Q high equal this plus this. Here, my output is Q low. What I want, I mean, in terms of what I want. What I want is what is desired from refrigerator to cool things down. So Q low. What I pay is electricity. I plug in the refrigerator in the. So this is reversed to this. Became a refrigerator or heat pump. Okay, guys? Make sense? Okay, guys? So what is COP, guys, for refrigerator? What is desired? What I want? Q low. What I paid is W.net in. This is supposed to be in now, which was out in here. Or Q high over Q high minus Q low. 0.85 over 0.42, it's 1.38. Yes, we said COP can go for refrigerator from 0 to more than 1. It's okay. It's okay. 0.5, 1.5, 2.5, it's okay. But COP for heat pump must be greater than 1. Thermal efficiency always lower than 1. Thermal efficiency always lower than 1. 50%, 45%, 42%, 30%, 20%, some engines 20%. By the end of the course, I will give you some examples in our life with a very low efficiency and how bad we are in using the energies. COP refrigerator can be from 0 to 1, 2, 3.5, anything from 0 and more. Efficiency from 0 to 1, thermal efficiency. COP heat pump greater than 1. Heat pump, because it's Q high over W, it must be greater than 1 because Q high always greater than W.net. Heat pump, Q high, which is what I want, over what I paid, W.net in. Any question, guys? Any questions? Any question, guys? Hello?
No, I'm good.
Okay. Does anyone have any problem? If you don't have, we're going to go to next problem. Problem 3, page 5. Lecture 11, problem 3, page 5. Okay, 11.5. 11.5, like this. So this is, I'm going to read it with you. Read it first by yourself in your notes over here. This is a very interesting, important problem. I used to put it in even a midterm, sometimes in the finals, or both. So this problem is interesting because it has two things together. Look at this. A combination of heat engine derives heat pump. So we have heat engine, HE, heat engine, guys, is a device. We pay heat to get work. We pay heat to get work. This work, the minute out, is gonna drive a heat pump. Heat pump, I want Q dot high. So I have heat, get heat. So I have heat, get work, drive this heat pump to get another heat, and use also the waste of other source. A combination of heat engine drives heat pump. Heat engine, pay fuel, get work. Heat pump is opposite. Pay work, get energy, heat. Which not fuel, but get heat, energy. See figure 3, this one. So we have two things. Okay? The takes waste energy. Okay. The heat, both of them takes waste energy at 50 Celsius. Here, 50 Celsius, here is 50 Celsius. So this one, T high was 50 Celsius. Here, T low was 50 Celsius. So T high was 50 Celsius here, and T low was 50 Celsius there. Okay, guys? Okay? The heat engine rejects the heat at 30 degrees. So the ambient that the heat engine, HE, rejects the heat at 30 degrees. So now it was coming from 50 to 30. That's correct. And give you some work. This work will drive this heat pump. Take some lower energy from 50, dump it in the 150. So all the temperatures were given. All the temperatures given. So remember, heat engine, we can talk about thermal efficiency, but heat pump, we need to talk about. Can I say thermal efficiency, guys? Guys, I said that last lecture. I told you, please read it. Heat pump, we need to talk about. Can I say thermal efficiency? The answer is just yes or no.
No.
What we use? Correct. No, it's correct. So what is that? What we're supposed to use? Thermal efficiency or what? What other term we use to measure?
COP.
Exactly. So this engine, heat engine, we use efficiency. But this one we use COP, coefficient of performance, because this is one of the two special cases, refrigerator and heat pump. Refrigerator has COP, Q low of our work in. Heat pump, Q high of our work in. So this is COP. This is efficiency, thermal efficiency. Okay, guys, this is the measurements of the efficiencies or the performance of an engine. Okay, guys. The remainder QW2, which is here, goes into energy derivative to high energy. This is the remainder of here. It goes to higher energy, which is Q150. Sorry, bump it to the 150. If total waste energy was 5 megawatts, so data waste energy here, WQ dot W1 plus W dot W2 equal 5 megawatt. So total waste energy, we have waste energy here. Let's say QW1. And here QW2. This is waste energy and this is waste energy. Both are 50 degrees. The same source. Some energy, give it to the heat energy. Some energy, give it to the heat pump. The total waste energy, 5 megawatt. It means this W1 plus this heat at W2 equal, we can give it any name, but here we call it waste 1, waste 2, W1, W2. The total waste, 5 megawatt. Find the rate of energy delivered at higher, find Q high. This is Q high. Find the rate of energy, Q dot, delivered at higher temperature here. Okay? Again, this one, between waste, this is waste. Energy, we don't want it. It's like some kind of waste energy, we don't want it. So I use it to drive heat engine, get some work. This work will drive a heat pump to get another higher temperature, using the same wastes, two wastes here. The total waste energy were 55 megawatt, while the temperature at everywhere were given. Temperature here, temperature there. So this is T low of heat engine. This is T high of heat engine. This is T low of heat pump. This is T high of heat pump. So this is heat pump. This is heat engine. Okay, guys? Okay?
Yeah.
Okay, let's stop this. We need now Q dot high. This problem, it was interesting problem. Let's draw everything back. This is the way we read the problem. But of course, because you're supposed to read, and as I said before, oh, I forgot the mic. Sorry, I forgot the mic. Can you hear me, guys, now?
Yeah.
I forgot the mic. My ears get warmed, you know, like heat pump in my ear. So we have here problem lecture 11, problem 3. It's different. It's not in the textbook. I pick up for you some problems from other sources. So we have here combined heat engine and heat pump. So we have heat engine. We call it he, not she. So we have here waste energy, W1. We have temperature here was 50 Celsius from waste 1. Waste energy, the same waste energy, the same source, this one, but we used to use to write it in the top high. This is the low now. In another side, waste energy, which is at 50 Celsius, we call it waste 2. This is Q high for the heat engine. This is Q low for the HP. HP. I don't like HP. I like it as a printer, of course, but I don't like it as a laptop. My laptop is done. So here we have Q dot high. That's what we want. So this waste energy will drive heat engine and also dump energy from heat pump. So this W naught, let's say W out here is in here. So this W, we call W dot. We have here also Q low, which is gonna go to 30 Celsius. We don't care about it. We have Q high here, is gonna go to 150 Celsius. Everything here is ideal. So we have temperature here, here. This is the low, high. Low for both, high for both. This work is the same. For every engine, guys, for every engine, guys, you have two inputs. For example, if you want thermal efficiency, it's 1 minus Q low over Q high. If you know two things, you get thermal efficiency. W net, for example, out, which is W net here, it's Q high minus Q low. So if you know two things about any engine, you are safe. If you know two things about any engine, you know everything about this engine. So if this engine, we have T high and T low, and T high and T low. So you already know something. One thing is known, Q high over Q low, some kind of information here. So we need one thing here, and I wish to know one thing here. The work here drives here. It means I don't want something here. Something is, I know already something else. This, the same as this. So if I solve this problem, I can give the work back here. I have two temperatures, this is done. So this work, because it's overlap, the work out from here equal work in inside here, it means I don't need anything here. This is with me. This is with me. This is, I will get it from that, or opposite. So I want one thing, only one thing, to get everything here, which is W dot 1 plus W dot 2, Q dot W1 plus Q dot W2 equal 5 megawatt. This is the only thing I want. Something given, anything. Waste 1, waste 2, anything. Make sense? So any engine, we need two things, any two things, Q high, W naught net. Q low, Q high. efficiency and Q low. Any two things, you can get the rest. Let's write this down. Of course, W net out of heat engine equal W dot net in heat pump. We're gonna call it W dot. That's it. QW1 plus QW2 West 1 plus West 2 equal 5 megawatt. Okay. Because I have all the temperatures, I can have all the performance, either efficiency here or efficiency or COP there. Let's start for first one, heat engine. Heat engine, always efficiency, eta thermal, which is 1 minus Q low over Q high, which is Y minus T low over T high. Or if you want to write it in terms of work, work is better here. Work is better. W net. Why work is better? Because work here is equal work there. So let's write work W net, W dot over Q high. That's better, much better. And COP for the heat pump, we're gonna write it in terms of work and Q, and we're gonna get everything. So heat thermal, I don't know what is this. Q high here is this waste energy 1, which is somehow I know it, part of it. W net is W net from heat engine equal W net out in for the heat pump. T low I have it. T high I have it for the heat engine. I'm talking about heat engine. So I can get from here W net out from the heat engine is equal Q high times 1 minus T high, T low, which is 30 plus 273.15 divided by T low, which is T high, sorry, by 50 plus 2. So W dot net, it's what? Q high is W1. This is W1. Q dot W1, it's high, the high. Q W1 times, you can dot everywhere in this case. The dot, but this is not dot. Times the wrong number. What's the number? What's the number, guys? Number is 0.006189. Any problem, guys? This is the first equation. Okay, guys? Any question, guys?
Did you cross out the TH under the W dot?
This one?
No, the one to the left of it. Yeah, right there. Did you cross it out and change it? Or
No. I said this Q high is equal to Q dot W1, West 1.
Oh, okay.
That's equal to. Replace it by W1. I mean, I'm not crossing. I'm just saying equal to W1. Okay, guys? Actually, you can write from the beginning. Output over input. So what's the input? What's the input, guys? Q dot W1. That's it. Okay? When you write an equation, you can write it in terms of words. Like, for example, it's output over input. What is the output? W dot. What is the input? West 1. That's it. As I told you before, when you are in thermodynamics problem, if you find two unknowns, stop. This means you cannot do anything. Let's go to the other one. The heat pump, HP. It's a very good printer, but it's not very good laptop. Yeah. Sorry, I'm giving them bad reviews because I hate them. So heat pump, HP. It's exactly opposite to this. It's not have thermal efficiency. It has something else called COP. So COP is equal to, let's do something here, then go back. Heat pump, generally, it's output, like for example, Q high over W net, which is Q high over Q high minus Q low equal 1 over Q 1 minus Q low over Q high, or 1 over 1 minus T low over T high. So here we said before, the heat pump is output over input, the COP, correct? The W naught is Q high minus Q low. Divide by Q high, Q low everywhere. So 1 over Q high over Q high over Q high. It became 1 over 1 minus this over this. And this over this ideally is T low over T high. So this equals this. Or this equals this. Or this equals this. So this is good and this is good. So it means Q high over W net equal 1 over 1 minus T low over T high. This is for heat pump. Actually, if you notice, this is exactly this equation. Exactly. This is W dot over Q high. If you upside down, it will be exactly this equation. Q high over W is 1 over this. Correct? So this equation, exactly this equation. This is W over Q high, 1 minus T low over T high. If you reverse it, which became COP. So Q high over W dot, Q high over W dot equal 1 over this. Correct, guys? Correct, guys?
Correct.
So here, thermal efficiency, it's output over input. Here it's output over input, but output here, Q high. Output here, W dot. Input here, Q high. Output there is Q high. That's why equation is 1 over. So you can say eta thermal, it's 1 over COP, heat pump. That's very correct. And actually COP heat pump is COP refrigerator plus 1 also. So that somehow they are manipulated equation. Anyway, so here W dot net, it's just W dot like this. Q high here is what? Q high. Okay, guys? Guys? Hello?
Yeah, sounds good.
We can make it easier, but it's okay. Keep it now. If you want, guys, this Q high is this plus this. It's W dot plus W Q, sorry. This is better. This plus this equal this. So you can rewrite this to be 1 plus Q with 2 over W dot. That's better. This is much better. Why? Because this guy equal is equal 1 minus. What is T low here, guys? What is T low? What is T low here? Guys, what's T low? What is T low here, guys? In this heat pump, what is T low?
Is it 50?
Exactly. So 50 plus 273, of course. How about what is T high? What is T high, guys?
150.
150. Exactly. It's very easy. It's from the. So we can write W dot in terms of Q, W2. So if you calculate this number, subtract 1 over. So W dot equals something times QW2, which is which was 0.3094. 0.3094. This is equation. I cannot solve it. 2. Look at 1 and 2. What the relation between 1 and 2, guys? What the relationship between 1 and 2?
W dot.
It's the same, exactly. You can omit W dot. So you combine them together from the heat engine, you got W in terms of Q waste 1. From the other one, you get waste 2. Correct? W in terms of the waste 2. So you can make them equal. You can say QW1 times something equal QW2 times something. Correct? Correct, guys? This work the same as this work. So this equal this. That's it. Right hand side equal right hand side. Any questions?
So we're ultimately solving Q dot.
W1 and W2. Now we have two equations and two unknowns. Equation 1 here, equation 2 there. So W1 dot QW1 Q dot W2, and here QW1 dot and QW dot 2, it's two equations in two unknowns. Using your calculator, you will find out Q dot W1 equal Q dot W2 equal. Both of them lower than 5 megawatt, and they are respectively 0.833 megawatt, while the other one is 4.166 megawatt. The two waste energy I can get. Again, guys, we have heat engine, we have heat engine, we have all the temperatures. It means I can write the work and Q high in terms of temperature. So the work in terms of Q high and temperature. That's I get something related to this and work. And this work, the same as other work. So I wish I can write this work in terms of this one or this one. So I write the other equation. So the work in terms of the other one. This work is the same as this work. They are equal. It means the two right-hand sides are equals. This means I can say this equal to that. I got one equation. Solve this simultaneously with this. You can get QW1, QW2, or Q dot W1 and Q dot W2. Now I want this. Still, I want this, guys. I want this. This is what required from the problem. I get this, yes. I got this, yes. Now, what should I do, guys? If I want this, I need W dot and this. So I have this guy, 4.166. I want this guy. How can I get it, guys? How can I get W dot, for example, now? W dot I get it from where? What equation on the board? I can get W dot. From where? From where, guys?
The equations we just used earlier to
Exactly.
relate
This
Q
one.
dot.
Equation number 1 or equation number 2, both are the same. So from any of them, you can get W dot, which is about, I think, 1.3 megawatt. So use that equation 1 or equation 2. So you can get, maybe I switch between them. Maybe this is 1, maybe this is 2. Oh, actually, this is correct. And maybe this is 2 and this is 1. Maybe I switch. So from any of these, substitute back, you can get W dot, which is 1.3 megawatt. For example, plus W with 2. No, it was correct. It was correct. This is W1. This is W2. So this plus this, it's 5.4. So Q high is 5.4 megawatt. Okay, guys? Is it hard or easy? Read it again. Read the problem again, please. Because I have all the temperatures. I need one thing here and one thing here. For example, if I told you I have Q low, from Q low and temperature, you can get Q high. From Q high and Q low, you can get work. If you had temperatures here. I need one thing, only one thing. If I know anything like W, I can get, for example, from W, Q low over Q high, and W, I can get Q high. How? Efficiency or COP. Here's COP. So I can get one of them. This, for example, one. From this temperature, I can get again this one. From this and this, I can get this one. So from one thing plus temperatures, I can get everything. But this work equal this work. It means I don't need anything here. If I solve this problem, I can get work, give it back to here. I have temperature, I can get this Q low and Q high. So I need one thing. So what is given? The total waste. Only one input. Plus all the temperature, I can get everything in this problem. From the first one, heat engine, this heat engine. What I want to get the work from here. I want to get the work from here and equate them. So work from here equal work from here. The work from here in terms of QW1. The work from there in terms of QW2. Why? To get one equation between W1 and W2, these Q's. And I have another equation, so two equations in two unknowns. High school problem, even elementary school problem. Two equations in two unknowns. So get W1 in terms of Q low, Q high here, which is waste 1. W here in terms of Q low, which is W2 here. So you can get this in terms of this. And you have this equation, two equations in two unknowns. You can get QW1, so you can get anything of the problem. So I only have this in the problem, only this. No other work. This is not given explicitly, not given explicitly, not given explicitly, not given. But I get everything with just one information because the work here drive there. Okay, guys? The final equation of Q high is Q high equal W dot plus Q low. Here, for example, Q high, this one, always equal this plus this. I have this, which is QW2. I want to get this guy. Yes, I can get it from this equation or that equation. So this Q low plus W dot equal Q high. Guys, for almost 3 lectures now, I'm saying the same equation. Q high equal Q low plus W dot. Yeah, Q high equal W dot plus Q low. Here is Q high is Q high, Q low is QW2, and work is work. So that's it.